Welcome to the comprehensive guide on Scikit-learn interview questions. Scikit-learn is one of the most popular Python machine learning libraries, and mastering it is essential for any data science or machine learning role. Throughout this presentation, you'll learn about the fundamental concepts, algorithms, and practical implementations that frequently appear in technical interviews. Whether you're preparing for your first machine learning position or advancing your career, understanding these core concepts will give you the confidence to tackle any Scikit-learn-related question. Machine learning with Scikit-learn revolves around four core areas. Classification involves predicting categorical outcomes, like determining whether an email is spam or not spam. Regression focuses on predicting continuous numerical values, such as house prices or stock values. Clustering is an unsupervised learning technique that groups similar data points together without predefined labels. Preprocessing encompasses all the data preparation steps needed before training a model, including scaling features, handling missing values, and encoding categorical variables. These four areas form the foundation of most machine learning workflows. Scikit-learn is an open-source machine learning library built specifically for Python. It's constructed on top of fundamental scientific computing libraries like NumPy, SciPy, and Matplotlib, making it both powerful and accessible. The library provides simple and efficient tools for data mining and data analysis, with a consistent interface across all algorithms. The basic import structure starts with importing specific modules like datasets for sample data, model selection for splitting data, and various algorithm modules like Ensemble for advanced techniques like random forest. This consistent API design makes it easy to switch between different algorithms while maintaining the same workflow. Classification algorithms predict discrete categories or classes. Random forest is an ensemble method that combines multiple decision trees to make more accurate predictions and reduce overfitting. Support vector machine finds the optimal boundary between different classes by maximizing the margin between them. Logistic regression, despite its name, is a classification algorithm that uses the logistic function to model probabilities. K-nearest neighbors classifies data points based on the majority class of their nearest neighbors. The example code shows how to create a random forest classifier with 100 estimators, train it on training data, make predictions on test data, and evaluate accuracy using the accuracy score metric. Regression algorithms predict continuous numerical values rather than discrete categories. Linear regression finds the best straight line through data points to predict target values based on input features. Random forest regressor applies the ensemble approach to regression problems, combining multiple decision trees for more robust predictions. Support vector regression extends the SVM concept to continuous outcomes by finding a function that approximates the relationship between features and targets. Ridge regression adds regularization to linear regression to prevent overfitting by penalizing large coefficients. The code example demonstrates creating a linear regression model, training it with fit method, making predictions, and evaluating performance using mean squared error. Clustering algorithms group similar data points together without using predefined labels, making them unsupervised learning techniques. K-means partitions data into K-clusters by finding centroids that minimize the distance to cluster members. Hierarchical clustering builds a tree of clusters by either merging smaller clusters or splitting larger ones. DBSCAN identifies clusters of varying shapes and sizes while automatically detecting outliers as noise points. Gaussian mixture models assume data comes from a mixture of Gaussian distributions and can handle overlapping clusters. The example shows creating a K-means model with 3 clusters, fitting and predicting cluster assignments in one step, and evaluating clustering quality using the silhouette score. Data preprocessing is crucial for preparing raw data for machine learning algorithms. Feature scaling ensures all features have similar ranges, preventing features with larger scales from dominating the model. Standard scalar transforms features to have zero mean and unit variance. Label encoding converts categorical text labels into numerical values that algorithms can process. Feature selection identifies and keeps only the most relevant features for the prediction task. Missing data handling involves strategies like imputation or removal of incomplete records. The code demonstrates using standard scalar to normalize feature values and label encoder to convert categorical target variables into numerical format. Model validation ensures your machine learning model performs well on unseen data. Train test split divides your dataset into separate portions for training and evaluation. Cross-validation provides more robust performance estimates by training and testing the model multiple times on different data subsets. Grid search systematically tests different hyperparameter combinations to find the optimal model configuration. Performance metrics like accuracy, precision, recall, and F1 score quantify how well your model performs. The example shows using 5-fold cross-validation to get multiple performance scores and grid search to find the best number of estimators parameter for a classifier. A standard machine learning workflow follows 5 essential steps. First, load and explore your data to understand its structure, distribution, and potential issues. Second, pre-process features by scaling, encoding, and cleaning the data. Third, split your data into training and testing sets to enable proper evaluation. Fourth, train your chosen model on the training data. Fifth, evaluate performance using appropriate metrics on the test set. Scikit-learn's pipeline class streamlines this process by chaining preprocessing steps with the final estimator, ensuring consistent transformations across training and prediction phases. The code shows creating a pipeline that combines standard scaling with support vector classification. Success in machine learning interviews requires both theoretical knowledge and practical skills. Practice coding by implementing algorithms from scratch and becoming fluent with Scikit-learn's API. Understanding the mathematical theory behind algorithms helps you explain when and why to use specific techniques. Master performance tuning through hyperparameter optimization, cross-validation, and model selection strategies. Gain real-world experience by working on projects with messy, imperfect data that reflects actual business problems. Remember that consistent practice and solid fundamentals are your keys to excelling in machine learning interviews. Focus on understanding concepts deeply rather than memorizing code, and always be prepared to explain your reasoning and trade-offs.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.